So, hello everyone, welcome back. This is our final lecture and it will be again conducted by Gonzalo, and he'll give us some details on the standard model and probably beyond as well.
I don't think I will have time to cover beyond.
Okay.
But yes, thanks, Ahmed, and thanks everyone for staying until the last class. Yes, today we're going to talk a little bit more on spontaneous symmetry breaking and the consequences it has, and also a very particular feature of the standard model, which is chirality. Uh, all of this belongs to the electroweak sector, which is the part we've discussed until now. But we will also talk a little bit about the last phase that the standard model features, which is a confined phase. And we will do it in the context of quantum chromodynamics. And then, we will put everything together and show what the standard model is. Okay, I think this should be a little bit less condensed than the last lecture, so I encourage you to ask questions, to raise your hand, and to have discussions. Okay, so I did not tell you anything about fermions at the moment, but in the standard model there are many fermions, and it turns out there is a very particular behavior of these fermions. So let's talk a little bit about that, about spontaneous symmetry breaking and chiral fermions. So the idea is the standard model is chiral. In the sense that it treats differently left and right-handed fermions. The natural language to describe this is in terms of Weyl spinors. Okay, so I'm talking about left and right-handed fermions, so you might be asking yourself, what am I talking about? So this is the first thing we need to cover. What is this thing about Weyl spinors and chirality? So what is the idea? In Ratul's lecture, I believe, we derived the Dirac equation by looking for a relativistic generalization of the Schrödinger equation. This is more or less the historical path. Somehow a relativistic Schrödinger equation. And then you found that the algebra behaves in such a way that it needs, the equation needs to act on objects which have 4 or more components. And these were the Dirac fermions. So you first looked for the equation and then found the objects which it acts on and understood the Dirac fermions as a collection of particle and antiparticle. Dirac spinors, Dirac, not Dirac. And then you study the behavior of these guys under Lorentz transformations. So they have nice properties. Under Lorentz transformations, which I'm going to call lambda. In particular, psi of x, I apply a Lorentz transformation to psi, where psi is a Dirac spinor, and this goes to some matrix acting on psi and the inverse core. And this matrix S could be written as an exponential. The details of this are not really important. They can be written as the exponential of some generators of rotations or of Lorentz transformations. And what does matter is the following, is that these generators have this shape. So they are block diagonal. They are antisymmetric. And they are written in terms of Pauli matrices, where I think all of these objects, sigma and epsilon, we introduced in the last lecture. So the block diagonal form suggests that the Dirac spinor is made up or is composed of two more fundamental objects, which is what we call Weil spinors. Okay. So I write my Dirac fermion psi in terms of a left-handed and a right-handed Weil spinor. Where psi L are two-dimensional spinors. And so they have the right degrees of freedom to describe a fermion of spin 1/2, spin up or spin down. Now recall or note that psi left and psi right have opposite behavior and their boosts, which is this S0I I was showing before, but same under rotations. Sij. In addition, or in particular, no, in addition, I like it. One can show, and you might consider this an exercise, that a parity operation that is x goes to minus x maps left-handed to right-handed and vice versa. Which is the reason why we call them left and right-handed. If I look at myself in a mirror and I move my right hand, the mirror is moving its left hand. This is the reason why we call them left and right-handed, because parity maps one to each other. Now, in the modern understanding of quantum field theory, or the modern understanding of quantum field theory is in terms of symmetries. And what we have just described is the symmetries of these objects under the action of the Lorentz group, which we believe is a fundamental symmetry of nature. We could have taken the opposite route than the one we took in the lectures. In particular, we could study what are the most general Lorentz transformations, type of Lorentz transformations, and which kind of objects have nice properties under these Lorentz transformations. From there, we can learn about the existence of scalars, fermions, vectors, and so on. Gravitons as well, most importantly. And from those objects, try to construct the most general renormalizable action, or the most general renormalizable Lagrangian featuring them. And then you will be taken immediately to the Dirac equation if you look for the most general thing with fermions. This is the more modern understanding of quantum field theory, just in terms of symmetries. The symmetries determine the dynamics of the system. So let me write that down. In the modern understanding of quantum field theory, in terms of symmetries, which in this case is Lorentz invariance, one would naturally find Weil spinors for, oh, I should have said, I might, did I not say? Ah, yes, this psi L and R are Weil spinors. Weil spinors as fundamental and then build the Dirac action as the most general renormalizable Folding patch. Okay, so let me give you this Lagrangian in terms of these variables, which will be useful later. So the Lagrangian, we know it is the Dirac Lagrangian. Let me not mess that up. Factor of I. So if I break this Lagrangian into pieces, I will find this quantity. I will explain the notation in a second. Okay, so this is the action. This is the Iraq action where I have defined sigma mu equals the identity. It's a 4-vector with the identity and the sigma matrices. So it's a vector of matrices if you want. And sigma bar is the same thing with a minus sign in the spatial components. Okay. So in particular, notice how the psi L and psi R mix to give a mass term for the fermion. This will be very important in what follows. So now we can talk about chiral theories. We say that a gauge theory is chiral if the left and right handed Weil fermions transform in different representations. Ah, I guess you don't know what the representation is. Transform in different ways, let me say that. Under gauge transformations. So let's see an example of this. And I have to warn you, this example is very sick. It does not work. It is not a consistent theory at the quantum level. But at the classical level, I can write it down and we can discuss the more important details. All the physics that is featured here is then featured in the SU2 cross U1 theory that is a standard model, or that is a part of the standard model. But this is the simplest thing we can write. So let's do it. Just with this warning that the theory is actually anomalous, so you shouldn't trust it. But it illustrates very well the mechanism I'm thinking of. Then I will have a little bit to say about anomalies later. Okay, so having said that, consider the U1 theory of a complex scalar a charged left-handed spinor and an uncharged right-handed spinor. Then, again, the most general renormalizable Lagrangian. I have to add a note actually. with this field content and symmetry. Is well, remember renormalizable, what morally what something renormalizable was we discussed in the end of last lecture, uh, which doesn't have too many dimensions, yeah, morally. So this is a Lagrangian minus 1/4. I think new. Also, I believe last time I was getting the wrong signs for the kinetic terms, so I apologize for that. So we have kinetic terms, a potential for the scalar, a kinetic term with a covariant derivative for the left-handed spinor, and an ordinary derivative uh, for the right-handed spinor. And there is still one more term compatible with gauge invariance that I can write, which is this one. Plus Hermitian contract. To make this more explicit, let me write what is the symmetry transformation we are thinking of. So we have written the usual field strength for my gauge field. This is abelian, so it only has these two terms. A covariant derivative for the scalar. For the left-handed fermion only. There is no, notice, no covariant derivative for psi r. And nevertheless, at the classical level, this is a consistent theory because there is a gauge invariance under these transformations. For arbitrary alpha. So psi r simply goes to itself. It's not charged under the gauge group. Psi L receives a phase. And the scalar receives the opposite phase. So that the Yukawa coupling, oh, sorry, this is called a Yukawa interaction, and the Y is called a Yukawa. Okay, and this combination here is gauge invariant. I might have messed up a sign. Let me question whether there is a plus or a minus actually. But the idea is if I choose the appropriate charge, then I can build this fermion-fermion scalar interaction, and it is compatible with H invariance. What is not compatible with H invariance, however, is a fermion mass. Because I would need something like psi L bar psi R to get a mass, and this transforms to give me to the alpha. Which is not gauge invariant. So I cannot put this combination in the Lagrangian, not by itself at least. Now, does this change upon spontaneous symmetry breaking? And the answer is yes. So take the usual spontaneous symmetry breaking potential of the last time, and find in unitary gauge the following behavior. So we have a kinetic term, and the kinetic part of the Lagrangian, which is only the only part I'm gonna choose. Well, let me. As usual, I can parameterize my fluctuations as I want. So I choose this parameterization. In unitary gauge, I can get rid of the term of the exponential, which is the part that is going to be eaten by the vector field. And the dynamics will be governed only by, the only scalar in the game will be the field eta, which is a Higgs field. So what happens to the Yukawa couplings? Remember we had psi L, phi, psi R times Y. So when the field gets its vacuum expectation value, we get Y times V, psi L, psi R, plus Y times eta of X over root 2 psi L, psi R. And similarly for the Hermitian conjugate. So the fermion fields also acquire a mass which is proportional to the strength of the Yukawa coupling and the strength of spontaneous symmetry breaking, which was given by V. Which was previously forbidden by gauge invariance. And of course, a coupling to the Higgs. So to be concrete, the kinetic term or the kinetic part of the Lagrangian is so the same thing I've written before. So we have a massive vector. We have a massive real scalar. And we have two massive Weyl spins, which again adds up because a massive fermion and a massless fermion have the same number of degrees of freedom. This is like the scalars, but unlike the vectors. Remember, those only have two. The massless vector has only 2 degrees of freedom, whereas the massive one has 3. And as before, as usual, the massive vector has eaten up the good big Olson boson of this U1 that is spontaneously broken. But the fermions have also acquired a mass through spontaneous symmetry breaking of this theory of this symmetry. And this is what happens in the standard model. Fermions get masses via Yukawa couplings that when the Higgs boson gets a vacuum expectation value, the fermions get a mass. A mass that depends on the strength of this Y, and understanding what is the plethora of Ys or why the fermions have so different masses is one of the open questions of the standard model. Okay. So some concluding remarks on chiral theories. I'm just going to be very descriptive here and talk a little bit about anomalies. So anomalous symmetries are symmetries in the classical sense. So the action is invariant, but are broken at the quantum level. What that means is that if I write the path integral, say for two fermions, the measures transforms more trivially under the sea. And why should we care? Well, we should care because chiral theories tend to be anomalous. And this can be a very big problem. Whether a chiral theory is anomalous depends on the charges. The standard model is anomaly free, or the SU2 of the standard model. And this is because there is a non-trivial, if you want, choice of charges that is satisfied. So the standard model is a consistent theory. I should say that gauge anomalies, and you can see, for instance, I think in this book, probably in any book on quantum theory, but I am thinking on Burgess and Moore standard model book. I think there is a long discussion there of anomalies. Now, gauge anomalies render inconsistent theories. Because there is a loss of unitarity, while global anomalies are useful in understanding the non-perturbative structure of quantum field theory. If you want to learn more about this, I recommend that you read David Tong's notes on gauge theories and supersymmetry. I would actually go a little bit farther and recommend all sets of notes he's written because they are free in his website and they are very, very, very good. Okay, so it's a bit early, but I am not at the middle, but I'm gonna change gears now and discuss QCD. So I think it's a good time for a short break. Maybe some questions.
Yeah, sure. I'll pause the recording.
Okay, so let us now change gears and discuss the last of the phases we will need to consider in order to describe the standard model. So this is a confined phase. And it will be useful to talk about it in the context of QCD or quantum chromodynamics. Quantum chromodynamics. Okay, so far we have discussed the Coulomb phase, and the Higgs phase of gauge theories. So the Coulomb is the unbroken. For instance, the U1 of electromagnetism is in its Coulomb phase, which is why it's called Coulomb phase, no? Because it leads to a Coulomb potential and so on. And the Higgs phase, which is a broken phase. And the question is, are there more phases of gauge theories that are featured by the standard model? And of course, this section, the title of this section tells us that this is the case. So there is one more phase that is featured in the standard model. The confined phase. Okay, so let me start the discussion by combining a few facts to warm up. So we have some facts. First of all, the only forces we observe at our energy scales. Remember, an energy scale is the same as a wavelength, no? So, in our day-to-day life, are gravity and EM, which is short for electromagnetism. That we don't observe the weak force we, as in myself, not we in experiments, we do observe weak forces in experiments. And these scales is explained by spontaneous symmetry breaking and the Higgs mechanism. The mediators get masses, and so we cannot excite them at low energies. The reason why we don't observe quantum chromodynamics in our day-to-day life is different. But let me make another observation before. Attractive forces form bound states, which is again nothing new. We know that planets in the solar system are bounded are bounded gravitationally, or atoms are bounded electromagnetically. And note, in the case of atoms, to give electrically neutral uh, states. Okay, another fact. QCD is a gauge theory with SU3 gauge group. That is, there are 8 generators or 8 gauge bosons and 3 charges, which we call colors. This, of course, has nothing to do with colors, right? We're talking about very, very, very high energies. And color is a wavelength, and so an energy, which has nothing to do with the discussion here. It's for historical reasons that they are called colors. And that doesn't matter a lot to us. Okay, so a related fact, and this is the last one, is that one can argue, and then again, I refer myself to the book of Burgess and Moore, in particular to chapter 8, and you will see how the math of behind this works, that the interaction energy of a quark system is negative when the combinations are colorless. Where quarks are fermions charged under QCD. So what happens if I put all of these facts together? Well, this suggests, first of all, that QCD forms bound states. Why? Because if the interaction energy is negative, then the energy of the bound state is smaller than the energy of the isolated system. And nature tends to be lazy, it tends to reduce energy. So the combined system, the bound state is energetically preferred, and this is what will happen. The same story happens for planetary orbits or for the atom. So QCD forms bound states, and these are furthermore colorless. which could explain that or suggests that we only observe colorless objects, bound states, at low energies. And this is what happens, but there is something else we have to talk about. Why? Because we can see electrons freely. Uh, we can see charged particles, and we cannot see colored particles by themselves. We can observe electromagnetic charges in isolation, but not colored ones. And this is the question we would like to answer. So this is probably the most important part of the lecture today, is the confinement hypothesis. Which states that the only energy eigenstates of the QCD Hamiltonian with finite energy are color neutral. What does this mean? It means that you will never ever be able to see a color particle in isolation. It would cost you infinite energy, an infinite amount of energy. A related problem, which if you will solve, you will get $1 million, is the following. Related. Proving that there exists a Yang-Mills theory and at the quantum level, and that this does have a mass gap that is, well, we'll see, is Millennium Prize problem of the Clay Math Institute. Which is essentially proof that this finite energy is different than zero. If you prove it, you'll get $1 million. So maybe worth trying, maybe not. I'll leave it to your taste. Okay, so what does all of this mean? If the hypothesis is true, and this seems to be correct, at least this is what the experiments are telling us, although that's of course not enough for a mathematician to give you $1 million. What this means is that we cannot see colored states in isolation, at least at low energies. So let me give you some heuristics in order to understand this. So I could think of the QCD potential in this way. There is a Coulomb-like attraction at small distances, and this must be, or this, well, this is perturbative. It is perturbative in the sense that I can derive this Coulomb potential in the same way I can derive the electromagnetic potential in quantum field theory, which is something you can do. But there is this term which I really don't understand. This is a non-perturbative effect. And understanding or getting some idea of where this term comes from is the goal of today's lecture. Well, I guess I can plot the potential for you. So this is a Coulomb potential, and this is a linear potential. And what the actual potential does is going to be something like this. So that at very small scales, it behaves like Coulomb, and at very large scales, it tends to put the quarks together. It's very attractive. In particular, it costs a lot of energy to get up here. It costs a lot of energy to separate quarks. And when this energy gets too large, quark antiquark pairs are nucleated. And screen the original pair. What this means really is that if I start with a pair quark antiquark, at these distances, at very small distances, the energy is two times the mass of the quark minus alpha over r. So, it's we have this sort of bound state. But if I put them separate from each other, the energy density, if I put them at a distance L, the energy density is going to get large and large and large. The system is going to form a string, something that looks like a string, and this is how this is the birth of string theory, but I will definitely not have done to talk about that. But the idea is that once the energy gets too large, it costs less energy to have this per quark anti-quark. Okay. So, when the energy gets to be around 4 times the quark mass, the string breaks down, a quark anti-quark pair is nucleated, and I get two bound states, which again are colorless. And this is heuristically the reason why I will never be able to see these colorless quarks. It all comes from this sigma here. So how can we understand this? How can we understand this sigma in the framework of quantum field theory? This is asymptotic freedom. What is the main idea? What is the physics? The physics is that the coupling constants are energy dependent. That is length scale dependent. Depending in what is the energy scale that I'm probing the system with, or the energy scale at which I am asking questions, I will observe that the coupling is stronger or lighter. So let me write that down. Coupling constants are all but constants. They are energy dependent. And not the energy is the inverse of a wavelength. So there is length dependence here. But it depends on the length I'm probing, that the system behaves like it's weakly coupled or not, which translates back into this behavior with R that we were seeing before. So for instance, while the electromagnetic coupling decreases with energy, and this is a fact, the QCD coupling instead grows. Confinement occurs when the system gets strongly coupled. And this is how the confined phase works. So that was the physics. Let's do the math. So I've said that QCD is a gauge theory, so I should write the Young-Mills action. And I've chosen to define the electromagnetic field or the gauge field in such a way that the 1 over G squared is outside. Why? Because remember what Nabil taught us is that in the part integral formulation, what I need to do really is to do this integral over field configurations. So let me remind you of the saddle point approximation. Is that if I have a function of the form exponential of a number times a function, then if its number is very, very large, all contributions, and the function admits a minimum, then all contributions except the minimum of the function are exponentially suppressed. So I can very well approximate the integral by the fluctuations around the minimum, the regions close to the minimum. So I expand my function f of x and I get something like this. Okay, and that is an integral I know how to. In the path integral formulation, the saddle point approximation means that I can choose a configuration that minimizes the action, that extremizes the action, and then study small fluctuations around it, which is precisely what we have been doing throughout the whole lecture course. There was a classical field configuration that solves the equations of motion, that is, that solves that minimizes the action, and then we studied quantum fluctuations around this behavior, around this configuration. But what happens if the coupling gets strong? Well, if G is small, then 1 over G squared is very large, and I can trust the saddle point approximation. If G gets order 1, then the saddle point approximation is very bad, and in principle, all field configurations contribute to the path integral, and I don't really know what happens. And this is why QCD features this weird behavior that we didn't understand in quantum field theory, because it gets very non-perturbative. Okay, so let me write that down. So when G is order 1, all configurations contribute. And we don't know what happens. except in some supersymmetric cases. Again, see David Tong's notes. But because the real world at low energies is not supersymmetric, could be at high energies, and the symmetry being spontaneously broken, but definitely not at the energy scales we want to study today, we don't really know what happens. Okay, and this is the reason why we get this sigma of r. So remember, I was writing this sort of potential. This alpha over r was the perturbative behavior that I understand. It's the Coulomb one. It is perturbative. And this is the non-perturbative part. Here, the quantum fields start doing funny things. I don't have control, and I don't know what happens. So it seems that at some energy scale or at some length scale, QCD becomes strongly coupled. And we can compute this. We can calculate at which scale QCD becomes strongly coupled. To do so, you have to understand that couplings run. That is, coupling constants receive energy-dependent corrections energy-dependent quantum corrections. To see this, recall the kinetic term of Young-Mills, which gives the gauge propagator. It gives the propagator of the field. And I'm talking here in the language of the lecture of Nabil. So we have 1 over, let me call it G0 squared, F mu nu, with that trace and so on. Okay, and we could understand this propagator as the exchange of a photon from one point to the other one. The idea is that this quantity gets quantum corrections. These corrections being of this form. We have the classical part. And then we have loop corrections. Like we have loops and loops running in loops. Okay, and you can compute this with the Feynman rules you derived. So as I was saying, these contributions, because there is this G squared here, these contributions correct the coupling constant. Let me just give you the result. One can show that at one loop for a gauge theory SU with some number of colors coupled to NF fermions, the G squared at an energy equals mu equals this quantity. So let me just write it down and I will tell you what this means in a second. Okay, so the idea is that mu r lambda are energy scales. What this means is measure G at some energy lambda. That is, I am colliding particles at typical energies lambda. Then at energy mu, the coupling has changed. The effective coupling has changed, and we observe G of mu. Note this depends, or so whether at low energies, the coupling is stronger depends on the sign of the combination. Of the number of colors and the number of fermions that are coupled to the theory. In particular, and this is the beta function. In particular, electromagnetism is smaller at gets weaker at low energies. And SU3 of QCD gets larger. Now, experimentally, we know that G strong at 90 GeV, giga-electron volts, which is the mass of the set boson, is around 0.12 times 4 pi. And one can compute the scale at which QCD gets strongly coupled by taking the lambda, the G goes to infinity limit. And this energy scale is around the 200 MeV. Okay, so this is the last thing I want to say about QCD. So QCD is well described at high energies. At high energies, that depends in the energy of the particles I am using to prove the theory. Because remember the observables, that is what the observables of these theories are, as matrix elements and so on. Because it is well described at high energies by a weakly coupled gauge theory with SU3 gauge group and fermions. At the energy scales of lambda QCD, the description breaks down because it gets strongly coupled. And I need non-perturbative treatments, such as, for instance, lattice QCD. Which starts from the path integral and does all the computations in a computer without needing Feynman diagrams and so on. It is not worthy though that energy is much smaller than lambda QCD. There is an emergent effective description an effective weakly coupled description, which describes the physics of pions, if that means anything to you. And this is a chiral perturbation theory. And I think this is important to remark because, there is nothing in the standard model that tells us it should be the ultimate thing. In principle, if I were to probe higher and higher energies, I would be, or I could discover new and new particles whose effect at low energies is very small, negligible, or nothing. So the standard model is most likely an effective description of something else that goes on at high energies, maybe range of energies, in very much the same way as chiral perturbation theory can describe QCD at low energies, but the formulation is much different at high energies. Okay, so before I start with the standard model as such, I guess I should stop for questions. Could you explain more about non-perturbative? I wish. No, so okay. So the idea, this is the main idea. The weakly coupled description works because this g squared is very, very small, which means that 1 over g squared is very, very large. And so I can approximate this by fluctuations around a classical background plus corrections. So, okay, let me talk a little bit more about that. So in principle, that sum in the path integral I can approximate it by sum over all classical solutions of the equations of motion of the same thing, no, of the fluctuations. So that is the action of the fluctuations along the background. So, even the weakly coupled description has, even there are non-perturbative effects, which can be important even in the classical description. If there were more than one solution to the equations of motion, which for these very complicated equations of motion is true, for instance, you have solitons in Yang-Mills theories, then there will be contributions to your correlation functions, which are perturbative plus the sum over all other solutions. And notice all other solutions are weighted by 1 over g squared, right? The action of all of those guys are weighted by 1 over g squared, which does not admit a Taylor expansion. In particular, what that means is that, the perturbative expansion is essentially a Taylor expansion in g squared. However, this is trivial. The perturbative expansion of e to the minus 1 over g squared is always trivial in when g squared goes to 0. It's something that the perturbative expansion cannot capture. We have just seen an example of a non-perturbative effect. Another way of writing the equation I just showed for the running of the couplings is this one. If I ask for g squared to go to infinity at the energy mu, I should ask it to go to 1 in order to lose perturbative control, right? But I'm just gonna do this for I'm gonna take the limit to infinity for simplicity. Then what I find is that the energy scale mu, which is what I've called lambda QCD, equals what? Equals lambda, which is arbitrary, e to the I'm doing this, this should be, let me say 1 over beta g squared lambda something like this. Okay, the relative signs don't really matter for the present discussion because beta can have either sign. So don't worry about that. But what we see here is that I could never be able to do this by Feynman diagrams. This energy scale has appeared non-perturbatively. If I try to do the Taylor expansion of this quantity here on zero, I will never see it. It's always zero everywhere. So this is an effect of an unperturbative. This is how I understand the emergence of an unperturbative effect in QCD. And the idea is that all the configurations are merging together and all have the same weight, so all contribute to the path integral. So the semi-classical expansion does not work. I should not trust it. In the case of supersymmetric theories, I have so little freedom. I have so little freedom that most configurations are not allowed, and I can break this sum exactly into a sum over into a finite sum over contributions that I understand. If you want to read more about this, more on exact computations in quantum field theory, read about supersymmetric localization. I can't recall whether it's covered in Tong's notes, but you can see the book Mirror Symmetry by Bafa and friends. So it is a path integral that doesn't work. Yes, we don't know how to do computations. I mean, this is not a problem of the physics. It is a problem of us not knowing how to approximate in order to get the right physics, right? It's not that nature is doing, I don't know. Well, I guess it's doing something weird, but our description does not know how to deal with this behavior. But there is a behavior, and we emerge as in the low energy limit, right? We are made of protons and neutrons, which are composite bound states of quarks and gluons. So physics works. Our description breaks down, but physics keeps going on, and then at low energies, new effects arise. Okay, so with that, let me no problem. So let me tell you about the standard model. We have all the ingredients to describe the standard model now. So as in the other lecture, the standard model is a relativistic quantum field theory. It's a relativistic gauge chiral quantum field theory with gauge group G equals SU3 color times SU2 left for chiral fermions times U1 hypercharge with generators that I'm going to indicate as G mu big A, W mu small a, and B. This gauge theory is coupled to a complex scalar, which is a Higgs field, which spontaneously break SU2 left cross U1 hypercharge to U1 electromagnetism, where these are not equal, and you have time to explore this on the examples, on the exercises. And we also have a bunch of fermions, right and left-handed fermions, which we call quarks and leptons. Let me denote the charges in this way. Big A, small a, hypercharge. So this is for SU3, this is for SU2, and this is for the U1. We have, for instance, that the Higgs is not charged under QCD. It's a doublet under SU2, so it's a pair of complex fields, and this pair transform appropriately under SU2 transformations, and has hypercharge 1/2. So what we have is that the Higgs is a SU2 doublet, H plus H0, with no SU3 charge. And it is an useful exercise to check that H plus is charged under electromagnetism and H0 is not. By the way, the mass of the Higgs is around, I'm talking by memory, but I think it's 125 giga electron volts. So it's much higher than the QCD, than lambda QCD. Now, very interestingly, the fermionic matter is repeated in 3 so-called families. With equal quantum numbers, but different Yukawa couplings, and therefore masses. Oops. So these are the objects. We have quark doublets, up quark, down quark. They form an SU2 doublet. Charm quark and strange quark, they also form an SU2 doublet. Top quark and bottom quark, they also form an SU2 doublet, the left-handed ones. They have color charge under SU3, which we denote by a 3. They are a doublet under SU2, and they have some hypercharge. They have some charge under U1. The right-handed quarks are the same guys, just the right-handed counterpart. They have the same, the opposite charge under QCD. They are not charged under SU2, and they have some hypercharge. And similarly for the down components, we have DR, SR, bottom R. We transform under SU3, don't transform under SU2, and have some hypercharge. So notice has opposite the right-handed quarks have opposite SU3 charge, but completely different SU2 cross U1 behavior, which is what makes the standard model chiral. In addition, we have leptons, so these are the quarks, which are the guys that have charge under QCD, and there are also leptons. We have also an SU2, a family, 3 families of SU2 doublets. We have the family of neutrinos and the corresponding leptons. So we have electron, tau, electron, muon, and tau. Tau, lepton, sorry. Neutrino of tau type, left-handed, and tau, which is not charged under QCD, it's a doublet under SU2 and has some hypercharge. And we have right-handed electrons, which have no QCD charge, no SU2 charge, and some hypercharge. That is a standard model. Well, yeah, I don't have much time, so I will not talk about the parameters in the standard model. Let me just point out that we already know of beyond the standard model physics. Because the standard model as originally formulated does not have mass terms for neutrinos. However, neutrinos are measured to have masses. So neutrinos have a mass, and this is not explained by the standard model. This is actually not allowed in the standard model. The simplest solution is to have right-handed neutrinos that are very massive and behave like we would have again 3 families and no charge. There's more evidence. This has not been measured, and of course it will be very, very difficult indeed to measure because they don't have charge under anything that we know of. They would have to be very massive, although I have not explained that. But there is more. There is dark matter, which cannot be explained in the standard model. There is a cosmological constant problem. The standard model predicts a much larger cosmological constant. And there is, of course, gravity. We do not know how to formulate a quantum field theory for gravity at high energies. We know how to do it at low energies. And the most promising candidate to address some or all of these problems is string theory. I'm sure Fernando Quevedo will have a lot to talk about this, and I strongly recommend you to attend his seminar. But I think that's all I want to say. Well, let me add something, a small little detail. I have been talking about the most general normalizable Lagrangian, and I was lying a little bit. There are also theta terms in the Lagrangian of the standard model. That is a term of the form E mu nu rho sigma F mu nu F rho sigma. These terms do not affect the equations of motion, but nevertheless give physical effects and are important at the quantum level, as I welcome you to check in any standard model book. Okay, so now this is the end. Thanks everyone for your attention. And yeah, I hope you enjoyed the class. It's been a long way since the canonical quantization of the Klein-Gordon field. We have now described the best description we have of nature at the moment. But as I hope these last 5 minutes suggested, there is more, and there is a lot of physics to do. And as physicists, it is our job to give explanations to these questions. So thank you very much. I hope you enjoyed.
Thanks, Gonzalo. It was a very good lecture. And let me turn off the recording.